We've just defined the dimension of a vector space to be the size of any basis of that vector space. And we know, at least for finite dimensional vector spaces, that that's a good definition because we know that any two bases have the same size. In this video, we're going to compute the dimension of various vector spaces by finding bases. So let's begin with the example of matrices with trace 0. Let me explain what the trace of a matrix is. So if you have, for example, a 2 by 2 matrix that looks like this, then the trace is the sum of the elements on the leading diagonal. So the leading diagonal means this stuff, the 1, 1 entry, the 2, 2 entry, and so on. So the trace of this 2 by 2 matrix will be A plus D. So this set which we've defined here is the set of all 2 by 2 complex matrices whose trace is 0. And it so happens that that is a subspace of the vector space of all 2 by 2 complex matrices. So you should check the 3 subspace conditions yourself to verify that this really is a subspace. And if it's a subspace, then it's a vector space in its own right, so we can ask, what is the dimension of S? So that's our motivating problem. Dimension of S is what? How can we find it? Well, we know that the way to find a dimension is to find a basis. At least that's one way that you can always do it. So let's look for a basis of S. Well, it helps to think about what is the general form of an element of S. So a matrix X, so a 2 by 2 complex matrix, well, it belongs to S if and only if X has the following form, right? What can we say? We know that the 1, 1 entry plus the 2, 2 entry must be 0. And that's the only condition. So the two other elements can be absolutely anything. So every element of S looks like this. And in fact, every element that looks like that is in S. So something lies in S if and only if it has this form. It's equal to A, B, C minus A for some A, B, and C complex numbers. But we can use this general form to actually spot straight away a useful thing for having a basis. So remember, a basis is a linearly independent spanning sequence for your vector space. And we could rewrite this X here by saying that this is equal to A times 1, 0, 0 minus 1 plus B times 0, 1, 0, 0 plus C times 0, 0, 1, 0. So let's give these matrices some names. So this matrix here is going to be called H. This matrix here, 0, 1, 0, 0, is going to be called E. And this final matrix is going to be called F. And what we've now shown is that actually every element of S, is equal to a linear combination of H and E and F. So we wrote down what an arbitrary element of S looked like, and we've seen that that element is actually a linear combination A times H plus B times E plus C times F. So since those 3 matrices, H and E and F, since those matrices belong to S, this shows that H, E, F, this sequence, is a spanning sequence for S. So the reason that those matrices are in S is that if you add their diagonal elements, you get 0. For example, for H, you get 1 plus minus 1, which is 0. And for E, you get 0 plus 0, which is 0. And for C, you get 0 plus 0, which again is 0. So each of those matrices actually belongs to S, and we've seen that an arbitrary element of S is a linear combination of H and E and F, so they are a spanning sequence for S. So I think they're a basis, and I'm going to prove this by checking the other part of the basis condition, which is linear independence. So to prove that they're linearly independent, I have to take a linear combination equal to the 0 vector in my vector space and prove that actually the coefficients in that linear combination must be 0. So let's do, for linear independence, we'll suppose that let's say alpha times h plus beta times e plus gamma times f is equal to the 0 vector in my vector space, which would be just the 2 by 2 0 matrix for some alpha and beta and gamma complex numbers. So we have a complex vector space, so our scalars should be complex numbers. Well then, if you do the addition on the left-hand side of that equality, you get alpha minus alpha, and you get beta here, and you get gamma here, and that's equal to 0, 0, 0, 0. But of course that means the 1, 1 entry would tell me alpha is 0, the 1, 2 entry would tell me beta is 0, and the 2, 1 entry would tell me that gamma is equal to 0. So we've shown that if a linear combination of h, e, f is the 0 vector, then the scalars must be 0. So this shows that the sequence h, e, f is linearly independent, Li for short. Okay, we've shown it is a spanning sequence for S. We've shown that it is linearly independent, so it's a basis. And therefore, the dimension of S is the size of this basis, which is 3. Alright, so before we move on, let's look at something which actually tends to confuse people a little bit about what we did when we were using this method to look for a basis. So we wrote down the general form of an element of S, and then we spotted, at this stage here, we spotted that we could write that general element X as something times this thing H plus something times E plus something times F, and then H and E and F turned out to be a basis for our vector space. And often people think, well, you know, what if I wrote this slightly differently? What if I just said, what if I also wrote it as alpha times 1, so A times 1, 0, 0, 0 plus minus A times 0, 0, 0, minus 1 plus B times the same thing as before plus C times the same thing as before. Why can't I do this and then say, well, actually those 4 matrices are linearly independent, which is true, so those 4 matrices are a basis for S, and therefore the dimension of S is not 3 but is in fact 4. You know, why can't I do this? And the answer is that those 4 matrices are not a spanning sequence for S because they don't even belong to S. Like the first 2 things, this thing here and this thing here, those things are not in S. Let's just make this clear here. So this is not an element of S, and this also is not an element of S. So these things can't possibly be elements of a basis for S, because like the most basic property that a basis for a vector space has to have is it has to be a sequence of elements of that vector space. And those things are not elements of S, so they can't be part of a basis of S. So that's the reason that this alternative argument wouldn't work. Okay, let's look at some more examples. So we'll revisit one that we've already seen before, which is that we look at the vector space curly f of all functions from the real numbers to the real numbers. So 2 particular elements of that vector space are the sine function, that's a function from the real numbers to the real numbers, and the cosine function, which is also a function from the real numbers to the real numbers. So we can look at the span of those 2 functions, and the span of anything is always a subspace. So we proved this in a previous video when we learned about spanning sequences. So this thing which I've called T, the span of sine and cosine, is a subspace of my vector space F. So if it's a subspace, then it's a vector space in its own right, and we can ask what is its dimension. So the question again is, what is the dimension of T? So to find the dimension of T, the only way I know how to do it at the moment is to find a basis for T. But there is already a very obvious spanning sequence inside. We define T to be the span of the sine function and the cosine function. So by definition, the sine function and the cosine function form a spanning sequence for T. But also, we know that those two functions as elements of f are linearly independent. So we proved this before. If you've forgotten when this happened, it is example 4.6.4. I think I left this to you in the video as an exercise, but you can find it. You can find the details of the proof of linear independence written up in the lecture notes, section 4.6. So by that example, sine and cosine are linearly independent. So they are a spanning sequence for t. They are linearly independent. So the sequence sine and then cosine is a basis of t, and therefore the dimension of t is equal to 2. So if you're struggling to recall the linear independence proof, what we did is we took a linear combination. We said, okay, suppose alpha times sine plus beta times cosine is equal to the 0 function in f. And then if that's true, then, well, the 0 function is the function, the 0 vector in this vector space is the function which is always 0, the constant function which is 0. So you could evaluate for any real number and you'd always get 0. So alpha times sine of x plus beta times cosine of x will be equal to the real number 0 this time for any x and a real number. And by choosing appropriate values of x, you can show that alpha and beta must be 0, and therefore you have linear independence. Anyway, you can see the details by looking up example 4.6.4. So the dimension of that subspace is 2. And it's for our final example, return to some matrices. We're going to look at what called symmetric matrices. So a matrix is symmetric if and only if it's equal to its own transpose. And you can see that what we have here are our set U is the set of all 3 by 3 real matrices which are equal to their own transpose. So all 3 by 3 symmetric real matrices. So let's just use the method which we had before. So this, it turns out again, is a subspace of the vector space of all 3 by 3 real matrices. You should check the 3 subspace conditions yourself to verify that this really is a subspace, so that it is a vector space, and so we can talk about its dimension. And the question yet again is, what is the dimension of U? And the right way to think about this is to try and get a nice general form for a matrix in U. So let's think about the condition for a 3 by 3 matrix to belong to U. So X, a 3 by 3 matrix like this, then what its transpose will be is, remember how to do the transpose, you swap rows and columns. So the first column would be A, B, and C, that's the first row of X, and the second column would be D, E, F, because that's the second row, and the last column would be the last row of X. So in other words, you reflect in this leading diagonal that I mentioned earlier. You sort of do a mirror reflection in that line just there. Or alternatively, you just swap rows and columns. Okay, so that's what X transpose looks like. So X is equal to X transpose if and only if, what would happen? So we require, well, I can't say anything about A, but if we look at, for example, these two entries, the 1, 2 entries, then B must be equal to D. So I've got to have a B here, and then D must be equal to B. So I've got to have a B here. Similarly, if we look at these two entries, right, we have that C must be equal to G, or let's keep C, and then G must be the same as C. Okay, we get no condition on E, we get no condition on I, but we get that also similarly that H must be equal to F. So this is a description of an arbitrary matrix of U. A matrix X is in U if and only if it has this form. So A, B, C, E, F, I, a real number this time, since we were looking at 3 by 3 real matrices. So let's use the same trick as before and try and spot some matrices which belong to U, which we can use to write this matrix X. So we can find some matrices which we can write X as a linear combination of. So the easiest way to do this is to notice that this is A times E11. So I'm going to use this matrix, this notation here. So Eij is the 3 by 3 matrix with a 1 in position I, Ij, and zeros elsewhere. So E11 would have a 1 in its top left corner, and it would have zeros everywhere else. So it would be the matrix 1, 0, 0, 0, 0, 0, 0, 0, 0. Okay, that's going to be helpful because I can do things like this. So we would have B times E11, E12 plus E21, because that's we've got these two B's here and here in position 1, 2 and 2, 1, and we would have C times E13 plus E31 plus F times E23 plus E32 plus what have I missed? I've missed an E. Let's have an E here. E22, and there is an I times E33. Okay, just to be clear, my I here is a real number. It's just some arbitrary real number. It's not the square root of -1. Okay, and the point of writing it in this particular way is that all those matrices, so E11, E12 plus E21, and E13 plus E31, and E22, and E23 plus E32, and E33 are all in U. Those are all symmetric matrices. So if you imagine, for example, what E12 plus E21 looks like, let's just do an example of this. So if we look at E12 plus E21, that will be the matrix 0, 1, 0, 1, 0, 0, 0, 0, 1. So that matrix, 0, 0, 0 on the bottom row, that matrix is equal to its own transpose. And it's actually kind of easier to think about this if you think about, in general, what is the transpose of my matrix Eij? And the answer is that, well, think about it. What's the answer? So in general, Eij transpose will be equal to Eji. So E12 plus E21 all transpose would be E21 plus E12, which is the same as what you started off with, just written with the sum in the opposite order. So this really is E12 plus E21 really is a symmetric matrix. And similarly, all the other matrices that I've got there are symmetric. So they're all elements of U. And what our calculation shows is that those elements are a spanning sequence for U, because we've seen that any element of U can be written in this form, so like this thing here, and we've seen that any such matrix is a linear combination of the 6 matrices here. So those things are a spanning sequence. So this calculation right here showed that they were a spanning sequence for U because we wrote an arbitrary element of U as a linear combination of those 6 matrices. So the thing that you then need to do, if in order to prove that they are a basis, is to show that they are linearly independent. So having run out of space, I'm going to leave this to you. You can show that they are linearly independent just by the usual method, the same method that we used on our first example in this video. So take a linear combination of those things, suppose that that linear combination is equal to the 3 by 3 zero matrix, and deduce that actually A and B and C and E and F and I must be 0, so they're linearly independent. So when you've done this, you've got a basis of size 1, 2, 3, 4, 5, 6, so the dimension of U is equal to 6.